Hi guys, we're going to take a look at continuing Unit 1, Atomic Structure and Properties, and we're going to take a look at the composition of mixtures. So how do we analyze the amount of chemicals in a mixture? So we'll use percent composition to determine impurities in a mixture and the mass of the chemicals to determine the relative number of atoms in a substance. So as a reminder, percent composition or mass percent can be used in the analysis of chemicals in a mixture. We've used it so far just to look at elements within a particular compound. Now we're kind of expanding our viewpoint and saying, okay, what about multiple chemicals in a mixture? So the mass percent of a mixture is the mass of one chemical in the mixture divided by the mass of the total mixture. So we're looking at one particular chemical in the total mixture, and then we multiply by 100 to make it a percentage. So like all percentages, it's the part that we're looking at and analyzing out of the whole thing times 100. Because it's called mass percent, we want those units to be in grams or in mass. So here's an example. It says a mixture is determined to contain 1.50 moles of NaCl in a 100-gram sample of an unknown mixture. What is the percent by mass of sodium chloride in the mixture? So a couple of things we want to do. If we want to approach this, we've got sodium chloride, NaCl. It's part of some mixture, so it's mixed with at least one other chemical, if not multiple other ones. And we want to know what percentage of that mixture is just sodium chloride, okay? Is it half the mixture, 50%? Is it 75%? Is it 33%? What is the percentage of sodium chloride in that mixture? So the first thing we need is we need the units to be in common. We've got moles for NaCl, we've got grams for our sample. We need those to be the same so we can calculate this. So we first need them, it is a mass percent, so we want to do it in grams. So we're going to take our moles of NaCl and we're going to go ahead and get those to grams. Ooh, please excuse my handwriting here. I'm just using my finger to write on the screen. So our moles of NaCl, we want to go ahead and change from moles into grams. So we can use our periodic table and our calculator, which I should have, and calculate this. So the mass of sodium is 22.99. The mass of chlorine is 35.45. So if we add each of those together, since there's one of each, we get 58.44 grams. And it's a molar mass, so it's grams per mole or grams in 1 mole. So if I then multiply that by 1.5, we're going to get 87.66 grams of sodium chloride in our mixture here. Okay, 87.66 grams. So if we want to find its percent by mass, we have 87.66, our decimal, grams of sodium chloride divided by our total mass of the mixture. So sodium chloride is the part we're analyzing. Our whole thing would be the whole mixture, which is a 100-gram sample. Notice there is that decimal on your 100. That is telling us there's those zeros are significant, so we're going to keep that in mind. And then we are going to multiply by 100. So we're actually dividing by 100, and then we're multiplying by 100 because our sample is 100 grams. That actually makes our calculation very straightforward. So because this is a 100-gram sample, we have 87.66% of it is sodium chloride, right? Now, if that was 150-gram sample, we'd do 87 divided by 150 times 100. If it was a 20-gram sample, or, well, it can't be 20. It'd have to be something at least 87.66 or bigger. So we divide by whatever that total mass is of the mixture. So if we had the same kind of mixture, a consistent one, 87.66% of it would be that sodium chloride every time. All right, let's take a look at another example here. So this one gives us some information in a graph, and then here is our prompt. A mixture contains 20 liters of helium gas and 30 liters of hydrogen gas. what is the percent by mass of hydrogen in the mixture? So we don't have moles, we don't have grams, but we do have this volume in liters, and we have a graph. If we take a look at our graph, it gives us our volume on the vertical axis, on the y-axis, and then it relates it to our number of moles of gas. So we're going to use this graph just to help us. So sometimes this is how some AP questions are approached. They give you some other way of giving you the information and having you determine it. Okay. So in this case, 20 liters of hydrogen, or excuse me, of helium. If we go up to 20, that would be here, and we draw a line, and then we do this straight down as best we can. That looks like 0.9 moles of helium. Okay, and we can go ahead and convert that from moles, into grams using its molar mass. So helium has a mass of 4.00 on our periodic table. It's just 1 helium grams per mole. So we've got 0.9 times 4 gives us 3.6 grams of helium. So that's one of our chemicals. Okay, we're going to do the same thing with our hydrogen. Maybe pause and see if you can determine your mass of hydrogen and do that calculation. All right, let's check it out, see what we got. So 30 liters, we go over, we go down. Best we can, that's going to be about 1.3, I think. Yeah. So 1.3 moles of hydrogen, H2. 1 mole of hydrogen, its mass would be, there's 2 hydrogen atoms, so we do need to add that up. So in 1.01 is hydrogen, so 2.02 for H2. So 1.3 times 2.02 gives us, with 2 sig figs, 2.6 grams of hydrogen. All right, so we've got our mass of each of our chemicals. We've taken that step. Now our question is looking for the percent by mass of hydrogen in the mixture. So we're analyzing hydrogen in the total mixture. So if we want to find that percentage, we're going to take hydrogen's mass, 2.6 grams, and we need to divide it by the total mass of the mixture. So we have 3.6 plus 2.6, and we get 6.2 total. So we're adding up the mass of both of our chemicals there, 2.6 grams. Oops. And we want to multiply by 100 to make it a percentage. So 2.6 divided by 6.2 times 100, and we get 41.9%. We've only got 2 sig figs here, so that is really 42% if we round it. All right, so that's telling us if we have 20 liters of helium and 30 liters of hydrogen gas, 42% of our mass in that container is from hydrogen. 42% of the mass is from hydrogen. All right. So even though we look at this and say, well, we have more volume of hydrogen, it actually has less mass overall because helium gas weighs more. Okay, so that's something we can also see from this. All right, so we're going to take a look and continue with the purity of a substance. So how can we see if a sample we're given is just one thing, if it is pure, or if it has other contaminants in it? So a substance's purity can be determined by analyzing its percent composition. So if we look at that chemical's percent composition, that can help us see if our sample is pure or not. So here's an example question. A pure sample of calcium chloride should be 41% calcium by mass. So if we have just calcium chloride, it should only have 40% of its mass be calcium. The rest of that 60%-ish should be chlorine mass. So a student analyzes a sample of calcium chloride to determine if it's pure, right? If it's pure, we should get 40% calcium. But they find that it's 49% calcium. So which of the following is consistent with this data? So let's take a look at our options here and what's going on. We have that the sample contains only calcium chloride. If that was true, then these two values for calcium should match, right? So we can go ahead and eliminate that answer. We always want to try and eliminate answers in a multiple choice question to narrow down our chances of getting it correct and narrow down, kind of reduce our options of getting it wrong as well. Now, it would be good to have a periodic table handy to take a look at the rest. Now, if you notice, the rest of the things say that the sample contains another chemical and calcium chloride. Okay, so we know that calcium chloride is in there, but it has some sort of impurity that's raising the amount of calcium. Well, it's also good to think about what's happening to the other chemical. If there's more calcium, that means that there's less mass of the other chemical that's there. Okay, so let's look at the other compounds. We've got calcium fluoride, calcium iodide, and calcium bromide. They all have calcium in them, but they have another halogen. Okay, if we look at our periodic table, towards the right side, we've got fluorine. Ooh, that's a terrible F. Chlorine, bromine, Br, and iodine. Okay, so this is our one we know is in the mixture, calcium chloride. Now, is the other chemical, that impurity, is it going to be have fluorine, bromine, or iodine? That's our question. Well, again, if we have more calcium, that means we have less mass of whatever the other thing is. So if our other ion in our normal one is chlorine, then we need something with less mass to be the impurity, okay, with less mass of that negative ion. Okay, bromine and iodine both have more mass, right? We're adding mass. That's more heavy, right? So if I have more of that mass, then I'm going to have a lower mass of calcium. It's opposite. We want a higher mass of calcium and a lower mass of the other one. So that means that fluorine has to be our answer. Okay. The sample contains calcium fluoride. If I have calcium fluoride, then the fluorine has a lower mass than chlorine, so it's contributing less, and it's going to look like, and we're going to have more mass for calcium overall. More percentage of it will be from calcium, right? So that's how we kind of have to analyze these. We have to look at what do they have in common. Okay, we're talking about the calcium, but what else is in common about all the other options, and what are we really looking at, right? So it says when the mass percent is larger than it should be, so in this case, calcium's mass percent was larger than it should be, it was 49%, then the other element it's bonded to, its mass should be smaller, right? If one goes up, the other's got to go down because they're percentages. Everything has to add up to 100. So that's a good way we can analyze a multiple choice question like this. We don't have to do a whole bunch of calculating. We just have to think about it and eliminate some answers. Now let's try some more. Oh, and the opposite would be true, of course. If our mass percent was lower than it should be, then the other element's mass should be higher, right? So instead, if we had, instead of 49% for calcium, say we had 32%, right? It's lower. Then the bromine or iodine would be a more likely answer. Okay. All right, we're going to take a look at another example here and how we would approach this type of problem. So a student is given 200-gram samples, so same mass. Each mixture, or each is a mixture of only CH4 and CO2 gases. So we've got two containers, they've got the same gases in them, but they're in different proportions, different percentages, right? So same mass, same chemicals, different percentages. What information could be used to determine which mixture has a higher proportion of carbon dioxide? Okay, why don't you take a minute and think about this, think about, would we need to know percentages, masses, moles? What kind of information might help us? Maybe jot down, brainstorm some ideas, and then come back. All right, so hopefully you kind of thought through it. Maybe you have some ideas. So how would we approach this? So we want to know of our two mixtures, so here's our two containers, which one has more CO2, okay? So if we kind of think about these, we've got CH4 and CO2. We can do things like find the mass of carbon, the mass of hydrogen, the mass of oxygen in each, and those types of things can help us. The biggest one that's going to help us is that we would want to know the amount of the element that the two chemicals have in common. If we know how much carbon is in each, the percent or the mass, grams, of carbon in each of those containers, we will know which one has a higher proportion of CO2. Okay, well, why is that? So in this example, both have carbon. Knowing the mass of carbon in each mixture would help determine which chemical is in higher quantity. Now, in this little table here, we've got the molar mass of each. So this is just from our periodic table. It's not telling us the mass of the chemical in the actual container, but we have that molar mass. So let's analyze this. If there was more CH4 in the mixture, then the mixture would have a higher mass of carbon overall, because hydrogen has a really small mass and contributes less mass to the mixture. So if I have a whole bunch of CH4, then I'm going to have a whole lot of mass of carbon, right? Overall, higher percentage of carbon. If there was more carbon dioxide, CO2, then the mixture would have a smaller mass of carbon overall, because the oxygen has such a big mass. When we think about CO2, that has 2 oxygens. That's 32 grams for every 12 grams of carbon, right? That's almost 3 times as much. That's a lot. So if we have a lot of carbon dioxide, we're going to shrink the amount of carbon we have. Okay, so the one that, if we looked at these mixtures, if this one had, I don't know, 40 grams of carbon, and this one had 80 grams of carbon, the one with more CO2 would be the one with less carbon, because that oxygen is contributing so much mass to the mixture. Okay, so when we look, again, this is similar to that last example in that we're not having to do any calculations. We're just having to think about what are the other elements? How are they contributing to the mass? How is that going to give us clues to what's happening in our mixture? Okay, so they like to kind of include this type of thinking question on a P test as a multiple choice. So in this one, if it was a multiple choice, they might say, you know, the mass of carbon might be an option. The mass of oxygen, the mass of hydrogen, those would be options. Maybe, or it might say the volume of something, or it might say the percentage of hydrogen in it. There's going to be different options, right? We want to know the information about what they have in common, which is, in this case is the carbon. All right, let's take a look at one more example of a mixture and how we would approach this question. So the mass percent of carbon in pure glucose is 40%, okay? We know regular glucose is going to be 40% carbon, right? There's our carbon. A chemist analyzes the impure sample of glucose and determines that the mass percent of carbon is 38.2%, so just a little bit low. Which of the following impurities could account for the low mass percent of the carbon in the sample? So this is kind of going back to our thinking there. If our percentage is lower than it should be, then we need more of the other chemicals. So carbon is lower, so we need more hydrogen and more oxygen. Okay, so let's take a look. We've got ribose, okay? This has less carbon, less hydrogen, and less oxygen. than our glucose. So that doesn't really help us. It's not getting that exchange of one for the other. So that doesn't really work. Fructose, C6H12O6, an isomer of glucose. You notice that the chemical formulas are exactly the same. An isomer means it's the same atoms, they're just arranged differently. Okay, isomer. Iso means same. Okay. So like isotope might be a little more familiar, means the same element, but a different structure. So that doesn't really change anything. We're not getting less carbon, we're not getting more hydrogen, oxygen. Our next one here, we've got C12H22O11. We are getting more hydrogen and oxygen, but we're also getting more carbon. So again, that doesn't really help us. If this had water in it, it's not changing the amount of carbon, but it is adding hydrogen and oxygen. So that is the most logical answer. If carbon is lower than it should be, then we have to have more mass from the other elements. Okay? So that's our last example here. There's lots of different ways that mixtures can be approached. It's really about looking at, we can, oftentimes it might be asked about percent composition from data, and otherwise we're really just analyzing situations and seeing what's causing that change, what's a difference between mixtures. So it takes more just thinking and using your logic, using your periodic table to look at molar masses, that sort of thing. So there's some practice. Try that out, and we'll go from there. Thanks, guys. Don't forget to subscribe to my channel too. Bye.